to both of these amazing people that will be giving the lecture today to us. So Frans is based at Leiden Observatory and heads a group that pioneers cutting-edge optical tools for global telescopes and space missions to study exoplanets and potentially detect extraterrestrial life. His work encompasses advanced liquid crystal technology, wavefront sensing, spectroscopy, and polarimetry for high-contrast imaging. Notably, Frans developed a remote sensing method to identify homochirality as a universal life indicator, which would result in spin-offs in areas like area pollution and monitoring and innovative instrument design. And as for Hester, she's an air quality scientist at the Dutch National Institute of Public Health and the Environment, or RIVM for short. Became engaged in citizen science through the successful iSPEX project. This led her to co-found Measure Together, an initiative promoting citizen-led environmental measurements and their integration into official monitoring. Hester's involvement extends to various citizen science projects and leaderships roles in European associations focused on citizen science and air quality. So I'm gonna give the mic to you guys. So thank you so much for being here, and I hope our team will gather a lot from your lecture today.
All right. Well, thank you so much, and feel free to interrupt us. I mean, I gather we have an hour or so, and we really want to make this also a discussion and a dialogue. So ask questions or whatever, just by raising the hand in Zoom, for instance. So I'm not sure if it's a coincidence, but both Hester and I were originally astronomers, and I'm still officially an astronomer, and we somehow ended up in air pollution measurements and in citizen science. So it's our pleasure today to tell you at least a little bit of that story of how that came to be. There's certainly a lot of serendipity involved, and certainly also a lot of fun involved. So here you see this is, I think, already more than 10 years ago. You clearly see this is the Netherlands. This is flat and green and below sea level. Whereas usually as an astronomer, my territory is this. So this is high up and dry in the desert in Chile, where I work with these telescopes called the Very Large Telescope. And I, of course, don't do this alone. I do this together with a group of people, and we're involved in development for optics and then using that for observations of exoplanets, so planets orbiting other star than the sun. But there's also a lot of spin-off in the direction of Earth observation and citizen science and even art projects. So for astronomy, we're basically taking over the world. So our technology is in all these telescopes that you see here. And then if we point that at a single star, the star will kind of look like this. And we create dark holes so we can look next to these stars and find planets. And with another observing techniques, we can also switch off the light of this particular star and reveal that there is still a lot of dust orbiting this star. And this talk is a lot about dust and other aerosols in our own atmosphere. And in this case, we can see this dust due to the property of light that is called polarization, which you may have seen before if you have these Polaroid sunglasses. But in this case, the polarization of light is evidenced by the scattering of dust around the star in the middle. But if you look carefully, also the planet on the lower left there has a polarization signal, which we can actually interpret as coming due to dust orbiting that young planet. And in that dust disk, there's actually moons forming. So we're not only talking about exoplanets, we're talking about exomoons. And we're further developing this technique to also be able to see planets that would kind of look like the Earth orbiting other stars than the sun, by making use of the fact that the light coming from the star is unpolarized, as you see here, so it has no preferential direction. And if that light scatters in an atmosphere of our own planet or of another planet, it has this preferential direction, as you see here. In other words, it becomes polarized. And that's exactly the property that we're using for the instruments that we call SPEXone, that is now currently bolted on the PACE satellite at NASA, which will be launched by SpaceX in January, still on schedule, that will not look up at the stars, it will look down on Earth at these 5 different angles that you see here, and will scan over the entire atmosphere and surface over planet Earth, and in this way observe dust particles and other particles in our atmosphere. And just to get a little bit technical, so we only observe the light that initially came from the sun that gets scattered in our atmosphere, and we measure all the different properties of light that we can. We measure its spectrum, so the colors of the rainbow, almost literally invisible light. We measure its polarization properties, and we measure that for different angles, scattering angles from the sun. And if you do that, you can show that you can infer all kinds of properties of the particles that scatter that sunlight. So the amount of particles or the number density, the size distribution, is this big particles or tiny particles. We can even infer the chemical composition through the refractive index. So is this sand particles or soot or salt or whatever? And we can even say something about the shape. For instance, in volcanic ash, there's these very abrasive particles, or in clouds you have spherical particles. So this technique has kind of been developed for astronomy and planetary sciences, which we're now applying for Earth observation, which is very relevant for climate models and also for air pollution. So if you see this black hole over the Netherlands, this is where we live. There's lots of air pollution issues in the Netherlands, but there's several other black holes out there, and this air pollution can consist of particles, aerosol particles, and just by breathing in these particles, you can lose a year or more on your life expectancy, as is shown here. And it's actually the smallest particles that can penetrate your lungs and your bloodstream deeper and create all kinds of cardiovascular problems. So to fully understand what's going on here, we need to have more measurements, which is what we're doing also with citizen science. And in climate change, this comes from the IPCC climate report. The climate models are already extremely accurate, and this is kind of the state of our knowledge on climate change, with, of course, CO2 and global warming on the very top. As you see, there's still a little bit of an error bar in there, but it's clear that CO2 warms up our planet. The bar goes to the right. If you now zoom in on these things called aerosols and precursors, you see that there's bars going both left and right. And you also see that the error bars on the knowledge how much this warms or cools are pretty large. And this is due to the fact that these aerosol particles, they typically also scatter sunlight back into space. And in this way, they can help actually cool our climate. Also, if you look one further down, the cloud adjustment due to aerosols. So these dust particles, they make clouds. They make more clouds, they make whiter clouds, and clouds also reflect sunlight back into space. So that could be a good thing. But you can also consider this is masking the heating, the warming effects due to greenhouse gases such as CO2. You also see there's an effect to the right, which is due to soot. So black particles, they actually contain the heat, they do not scatter, and they change the energy balance. So the largest source of uncertainty is all these strange effects of dust particles and aerosols that we do not know extremely well. So we need to start measuring them. So we will start measuring them with our SPEXone instrument on the PACE satellite as of next January. But also with citizen science, we have started measuring these things. So also to get to stay a little bit technical, the measurement principle that we invented for SPEX and later also iSPEX is a bit peculiar. So that's why I wanted to introduce that with a little movie. What we actually measure in the end is on the bottom here, where you see light as a function of color. So imagine this is called a spectrum, basically color stretched out as a rainbow. And what we do is we print the information on the polarization on top of these spectra. So what we do in the setup here is glass plates. If you go through a glass plate at an angle, you create polarization, and you see this polarization nicely imprinted with, in fact, a sine curve on top of the spectrum. So this gives you a very accurate measurement in a single shot of the amount of polarization as a function of wavelength. And if you rotate this entire contraption, you see that also the phase of this pattern moves around, so you can measure the polarization orientation as well. So we have further developed this instrument and started testing this. This is again in the Netherlands during a measurement campaign. Our colleagues actually put this on an airplane, which used to be called a U-2. This used to be a spy plane at 20 kilometers altitude, but now a scientific plane. And then looking down on California, we measure both the colors and spectrum of the atmosphere and the landscape, and also the polarization, and infer the state of the atmosphere there in California. Of course, lots of things going on there. And the last couple of years, our colleagues at the Institute for Space Research, and actually also at Airbus, they have further developed this concept and turned this into a real satellite instrument that's currently fully integrated at the satellite and ready for launch. So this story is still continuing, but a parallel story emerged kind of, 12 years ago, when on a Friday afternoon, we were just playing around with our smartphones. I mean, you see, this is a very old type of iPhone. I mean, smartphones were still new and hip at the time. And we were playing with kind of the plastic version of this measurement technique. And this is kind of the birth of the iSPEX technique, where we showed that we can make a spectral measurement with a smartphone camera, but also with several other foils in front, we can do the polarization measurement as well. Well, this kind of got out of hand. We put a lot of students on this who 3D printed first prototypes, which was kind of the birth of iSPEX, again on kind of first generation iPhones back then only. And it got further out of hand when we won a big award. You see Hester here in the middle, and in our group of people. And then we had to spend all this money. So we built like 10,000 of these iPhone add-ons, and we did a big marketing campaign. So a lot of people received this to the letterbox, and we had developed the app and all that. And then we had to wait for a long time, because this measurement actually takes cloud-free skies. So if you have been to the Netherlands, you know how difficult it is to get cloud-free, beautiful weather all over the Netherlands. So we had to wait a couple of months. But then finally on July 8th in 2013, so that's slightly more than 10 years ago, we could finally call this first National Measurement Day. So we had some Dutch celebrities, our Dutch astronaut, our Dutch king, although I don't think this was the real king on Twitter back then, announced that we had this measurement day. So we started measuring. So we started measuring in the center of the Netherlands, which is kind of the reference site for all kinds of measurement and also for satellite validation. But in addition to us, literally thousands of people across the Netherlands were ready to perform measurements with us. So we had this kind of live map where we basically every second a measurement dropped on that map. So that made it very successful right away, that all these people were willing to contribute. So in the next day, we had a lot of publications already. Basically, all of our students ended up in the Dutch newspapers, which was very nice. But then we had a lot of these iSPEX measurements. So this is what a single photo taken through an iSPEX looks like. So on the left, you see the slit where the light enters the instrument. And on the right, you see the spectrum as recorded by the camera. And on top, again, you see this little modulation, which indicates the polarization. And in this case, the polarization of the blue sky. And the more aerosol, the more air pollution is in the sky, the lower this polarization, which in this case, we could measure just with a single smartphone photo. It's just that we had like 20,000 of these photos. And you can see here in a snapshot of our database that some of the data was more useful than others. For instance, the white iPhones had a lot of scattered light, which you see on the upper left. There were even some people who managed to put on the iSPEX backwards or produced selfies or whatever. So we had to read through the data, but in the end, a lot of the data was useful, and we could calibrate a lot of effects which were not in our low-cost plastic add-on, but actually in the in Apple's control of the camera back then. But when we did that, we could make movies like this. So what you see here on the left, this is of course the country of the Netherlands. Every single little triangle arrow that you see there is an individual iSPEX measurement. So the first thing that you see is that people are measuring everywhere. And basically the measurement density really follows the population density in the Netherlands. So you can make out individual cities like here, Amsterdam, Rotterdam, Leiden, The Hague, Utrecht here in the middle. But also in the rest of the Netherlands, people were participating. So we put a color on every measurement, and the color was kind of a first indication of the brightness of the sky as indicated by polarization. So brown means that the polarization is very low and there's a lot of dust in the sky, and bluish means that there's not a lot of dust in the sky. And what you see here is that individual measurements, there's quite a lot of scatter in these quantitative results, which is what we expected. And again, this is not due to the add-on, this is actually due to limited control over the iPhone cameras that we had back then. Now on the right, you see that the satellite that provides similar measurements comes over just once a day. And that has fairly large pixels. So what we did then with this beautiful, huge data set is we started aggregating the data and making maps. So what you see here on the left is for the afternoon of that measurement day. Every blue dot here is an individual measurement. And we started interpolating these measurements. So what you see is in the south of the Netherlands, there's clearly more dust in the sky than in the north. It's actually fairly typical for the Netherlands because there's a lot of industry in the south. And you see also the satellite snapshot on the right, you see a similar image with a lot of dust in the south and more clear skies in the north. It was just, in this case, we had actually a very similar situation as we have now. This was not air pollution at nose level. What we were measuring here with all of the Netherlands were smoke clouds coming from forest fires in Canada 2 weeks prior. So these smoke clouds had been blowing over the poles and they were blowing north to south over the Netherlands. This is what we measure, or what we can also measure with iSPEX, and which is validated by the satellite snapshot. So a couple of months later, we had another case of blue skies over the Netherlands. So a lot of people picked up their iSPEX and their phones again and provided measurements. And you can see right away that all the individual measurements have a much bluer color. So that means that the skies were a lot clearer on that day in September. Because there were no more forest fires. But again, when we aggregate the measurements, as we've done here on the left for the morning of the day and on the right for the afternoon of that day, you do see that there's some kind of yellow values, so some dust and indeed air pollution blowing over the Netherlands. And in this case, this was actually really real air pollution that came out of Germany and even out of Belgium and France that were blowing over the Netherlands. So in this case, we could blame the neighbors for this. But moreover, we could demonstrate indeed that this measurement principle works, both in a technical sense as well as in a social sense, because a lot of people were participating and also kept on participating even after the money for this project ran out. So this we put together in an actual scientific publication, for which the largest challenge was to give credit and authorship to all the citizen scientists who you actually see here in the middle, which we managed to have contribute to the actual scientific publication as well. And what we demonstrated there is that an individual iSPEX measurement can have a fairly large error bar, but on average, like 10 or 20 iSPEX measurements can be on par with the accuracy of our very well calibrated SPEX measurements. So that's extremely good news. What we also demonstrated is that we have a spatial resolution of about 2 kilometers, which is much better than what the typical satellite instrument does at like 20 kilometers or so. And in that way, we could actually have individual dust in the atmosphere curves for individual cities, for which satellites only provide kind of a daily snapshot. So we really proved the added values of these kind of citizen science measurements. But moreover, we actually interviewed a lot of our participants, and we had a big survey, and basically to understand how this works, and why people actually do want to participate. And that actually showed us that people are extremely eager to contribute to science in general. A subset of people actually very eager to contribute to measurements specifically of air pollution. And for that group of people, we actually in our communication, we have been very careful, because iSPEX measures these particulate matter in a completely different way than the kind of normal monitoring that Hester can tell you all about, on which legal norms are applied. And so we had to also disappoint some of these people that they could not sue the neighbor for barbecuing and exceeding air pollution norms. This was really a scientific experiment, but the vast majority of participants appreciated that and were extremely excited to do this. So this further got out of hand when this was actually discussed in Dutch Parliament. Not necessarily the scientific findings of iSPEX on pollution sources, but really the measurement principle and the citizen science principle of this project led to a whole lot of other similar initiatives that Hester will talk about. So this was in the Netherlands, and a couple of years later, we got a lot of attention in that year in international magazines. So this is in Nature. And then we got money from the EU to start rolling this out in all over Europe. And the UK was still part of Europe back then. So we rolled out a version of iSPEX, still with the old technology, in cities all over Europe. So here you may recognize Barcelona and London and Rome, and we had some major cities. But also then the money ran out fairly quickly. But what we demonstrated again is that people are extremely eager to do this. Then we were silent for a couple of years. And then 5 years ago, we got another grant out of Brussels to kind of re-engineer iSPEX. So very soon, I actually have one here. If you can see it on my camera, very soon we will be able to come out with iSPEX2, which is a much more carefully engineered version such that it fits on most kind of smartphone, because the original iSPEX only fit on the iPhone 4. Here we have kind of a generic universal design that should fit on most modern smartphones. And we also improved the way it does the measurements. And we have way more enhanced control over the smartphone cameras now. So we are actually convinced that iSPEX2 is a factor of many more accurate than the original iSPEX. So hopefully soon we will be able to roll that out, and we're spinning this off to our partner company, DDQ, and you can see all about that at the website, actually, ispex.org. So this is another look at that, just to show that with that 3D printable interface plate, we can interface to a range of different smartphones. So this is for air pollution measurements again, so particulate matter. But we expanded it also to be able to do experiments, so to do transmission spectroscopy of whatever water samples with stuff in it, which we can do at a lot of enhanced quality, because now we have very accurate calibrations of these cameras that are in a lot of smartphones. And in addition to air, we also do water color measurements now with iSPEX, and water color as a proxy of water pollution, for instance, to see if there are algal blooms or to measure the turbidity. And we have already started to validate iSPEX2 for these standard water measurements as well. So this is what we're now trying to roll out, and I'll give the floor to Hester now to tell her story of iSPEX and what happened next.
Yes, thank you, Frans. I rely on you to click through the presentation.
Yeah, just tell me to click. Yeah.
Yeah, maybe if you click now, you can see the animation. Yeah.
Excuse you guys for 1 minute. I just want to remind the participants, the ones listening, that you guys can interrupt the whole, I mean, not interrupt, but raise your hands at any time if you have any questions or anything you want to say. They are very much encouraging it. So yeah, please go on. Thank you.
Yes, please do give us your questions, or if you want to know something different, which we are, this is a short presentation and we have a lot to tell, because iSPEX, as Frans told you, was for me the first, my first experience in citizen science. And I was encouraged by the bosses in our company to do citizen science, and because what Frans showed is that participation is a big thing, and also from the higher you go in politics, the more they will will see the benefits of citizen science like things. And so I learned from iSPEX that citizen science is the way to go. It was the future. But I also had a few problems in this project. And one of them, if you go to the next slide, Frans, one of the things is what we do is not so much measuring air pollution, we are monitoring it. So if you're monitoring, you are conservative because you want to monitor air pollution in the same way for many, many years, so that you can compare different years and you can see what policy measures are doing to reduce the air pollution. And so we are measuring, so my colleagues, my direct colleagues, were measuring aerosols and particulate matter by weighing it. They basically had a big vacuum cleaner. They were sucking the air in and collecting the particulates on a filter and weighing that. And that is the way official air quality measurements are done. And official air quality measurements is what my institute is involved in. So the iSPEX measurements had this drawback that you cannot measure only in a clear sky, and you are not measuring PM10 and PM2.5. You are not weighing the particles. You are looking at a column through the air, and that is not quite exactly the same. So we decided that yes, citizen science is the future. We want to do citizen science, but it should be closer to our core business, which is measuring aerosols in a measure like PM10 and PM2.5. And that is why we decided to go on with citizen science, because we learned from iSPEX that it was very, people were very enthusiastic. But we used sensors like these. And these actually are also light scattering instruments like iSPEX. So we are measuring light scattered with this small instrument, but the results are directly converted to this micrograms per cubic meter. So if you go to the next one, Frans, this is what happens if you open this small instrument, then you can see what is inside, because it's actually a tiny light scattering experiment inside. It's just fascinating that they can make them this small, but there is actually inside this instrument a tiny laser. So if you look at the yellow cylinder, that is actually a red laser, and the light is scattered and detected by a photodiode, and the air is sucked in by a ventilator, which is similar to what you have in your computer. So there's a small ventilator sucking in the air, and when the particles cross the laser beam, the light is scattered in all directions, and this scattered light is detected by a photodiode. And it is just in this tiny, tiny instrument. So we go to the next slide. Then you can see the schematics of this instrument. And actually, apart from everything I just showed you, there's also a tiny microprocessor in there that calculates from this scattered light the weight of the particles per amount of air being sucked into this instrument. So that is how people in the Netherlands, and here's a map of the places where people in the Netherlands are doing these measurements. This is how there's also different types of sensors who do similar measurements, and there are around 2,000 to 3,000 people now in the Netherlands doing these measurements. And these are not our instruments. We have not given them instruments. They have bought these instruments and built a housing for it, and made sure it sent the measurements through Wi-Fi, and then they are sending the measurements to us. And we collect all the measurements in a database, which is called sensors.rvm.nl. And if you go to the next slide. Yeah, this is still, yeah. So why are all these people on different citizen science projects sending the data to us? Well, that is because we can add something to the data, because we are the people who are doing the official measurements of air quality. And so what we can add to the measurements is a comparison to the official measurements in the neighborhood. So if you look here, I selected one sensor on the map. And if you click on it, you can see the PM2.5 measurements, the particulate matter measurements for a week. And you can see that it fluctuates quite a lot. And the blue line is what the sensor, it's actually one of these, is measuring. And the orange and the red line are giving the official measurements, which are the closest official measurements to this sensor. And you can see that they have exactly the same type of behavior. So you can see from this comparison that this measurement is actually, that this sensor is actually working quite well. And this is what we give to the people. We give them some reference on how well is the sensor performing. So next slide. Yeah, so we can do an assessment of the quality of the data. We call it plausibility, because your sensor is not always the same as the reference measurement, but it could be because the sensor is not working properly, or it could be because the neighbor is having a barbecue, and your measurements are really quite different from other measurements in the neighborhood. So if you look at these two, the picture on the left is showing all sensors, and the picture on the right is showing the sensors without the ones that are performing badly. And you can see that the ones that are many of the very blue points, which means there's a few aerosols in the air, they are missing, because these are the sensors that are clogged up or not working properly. And the very red ones are also missing, because one of the problems I had with my sensor last summer was that a spider had made a web inside, and that was scattering light. So then you get 1,000, and I had to take it down and clean it actually. So this is what we give to the people, some estimate of the quality of and actually the quality of these tiny sensors. This sensor costs around 40 euros. This one maybe 15, and the quality you see is really not bad if you compare it to an official measurement instrument, which costs 20,000 euros. Next slide.
I have a question, sorry.
Yeah.
About how you guys determined the quality of the sensors. Was it like basically handwork? Were you determining that by yourself, or were the users kind of choosing the quality of their sensor? How do you determine that?
We determine the quality of the sensors using the official measurements, but also the other sensors in the neighborhood. So we make a group of, say, 20 sensors in the neighborhood, and we look at the ones that are outliers. So, and we look at every hour we have a data point. So we look at, is this sensor for a longer time differing from its neighboring sensors and or from the official measurements. Okay. So we can do this only because there are so many people participating.
I understand. Thank you.
Yeah. Okay. So we, of course, try to use the data also for our core business, which is also air quality modeling. And here you can see the difference between if you use only the official data points, which is around 80 measurement stations in the Netherlands, or whether you use all the sensor data as well. Then you have a couple of thousand points added, and you can see a lot more detail in the modeling. And you can see that this could be potentially of great benefit for local policymakers or people looking for sources of pollution on a more local scale. So, is this situation special in the Netherlands? Yeah, I guess it is. But you know, when you think about the Netherlands, I don't know if you ever been there, but the thing that strikes people most is the number of bikes. And there is actually more bikes in the Netherlands than people. If I walk down to the shed, I'm a family of 4. We have 7 bikes in the shed. So this is really true. We have a lot of bikes, and we have a lot of bike rides. And people are often speculating why that is. Are we more sporty? Are we having a flat country? Is the weather always so perfect for bike riding? And none of these things are actually predictors for the amount of bicycles in a country. The only thing that determines whether people ride a bike or not is the bike infrastructure. It's all about the infrastructure. If you make bicycle lanes, people will cycle. And that's simply the case. And if you look here at the map, you can see that the Netherlands and actually Flanders as well are completely covered by bicycle lanes, and that's why people cycle. And that is also the explanation of why people do air quality measurements. If you go to the next slide, actually what we built in Measure Together is a citizen science infrastructure. So we made a place where people could safely store their data. They could ask us, what kind of sensor should I use? Where should I send the data to? What can I do? Are there other people who can give me information about that? And we've made a place where we have visualization, and people can do an analysis of the data. And by building this infrastructure, you are actually making it so much easier for people to start their own citizen science experiments, that this sort of also works when, even if we are not providing people with these sensors, they are buying it themselves and making use of this infrastructure we built. Next one. So yeah, the Netherlands is not special, because also in Belgium they did the same, and you can see here a picture of really many people also in Flanders who are doing air quality measurements. The round symbols are the citizen science measurements, and the square ones are the official measurement stations. So they are doing a very similar thing. And Frans, now the next. Really, Sense Community deserves a shout out here, because they are a citizen science community, which is a bottom-up citizen science organization originating in Germany. But they have provided a manual to build sensor kits in 24 languages. And so what we actually do is, if people send us an email asking us, hey, how can I get an aerosol measurement kit, then we just tell them, hey, look at Sense Community website, and there you can find the description how to build a sensor kit for 50 euros. So many of the people and the citizen science projects in the Netherlands are actually using this. Not all of them, but many are using this kind of method. So wherever you live, you can just look in this on this website and see if your language is already in there. If it's not, you can translate it and add your own language and start your own citizen science project. Okay, well, really, the citizen science approach of doing air quality is conquering Europe. I'm also involved in a project which is called City Ops. I don't want to go in too much detail, but you see there's many countries involved. So we expect in the coming years to start projects measuring air quality in all these countries. And that's where I want to stop. And if you want to know more, please check out the website.
And unless there are very urgent questions, let me go to one more final slide. I have a lot of backup slides, but I'll just skip through quickly. I think this one may be a useful one to go through, and Hester may want to chime in. So we kind of stumbled into this citizen science thing 11 years ago, and we made many mistakes. So we hope that we learned a couple of lessons that we're actually trying to disseminate to whoever wants to know about it. So academics, but also certainly bottom-up organizations, which we're actually trying to connect as well. And actually, my first lesson learned is that citizen science is in no way cheap or easy. So there's still a lot of people think that we would just outsource our scientific practice to people who would do it for free. But actually setting it up and doing the communication and making it sustainable is a lot of work. But of course, you get a return on your investment in the sense that we will be able to measure and learn things that from just from us academics and government institutes we cannot do by ourselves. But to make it sustainable, and that's really the challenge that we're still facing 10 years later, we have to fully involve all participants and other stakeholders as early as possible in the definition process of whatever project you envisage. So you need community managers or community champions bottom up from the community to make sure that people will remain involved. And it's a fragile process, right? Because certainly for us academics, we also have to kind of let go of our power to find a synthesis between the questions that we want to have answers to put in a scientific publication, but certainly also involve the questions from the participants, which may be somewhat different. So that is certainly also a challenge. So both Hester and me, we like the technology, we like to geek out, but of course the technology itself is never really the driving force. It's a means to an end. What we found in iSPEX is that a lot of people have been approaching us through email and social media, and providing very rapid feedback was the only way that this worked, because a lot of people, it was not an easy measurement to do. So there's a lot of communication involved. And again, the largest challenge is to make it sustainable, which has to do with the motivation of the participants, but certainly also with funding. Certainly also all funding in academia is one project after the other. So every 4 years, you have to find new funding, which certainly hampered us with iSPEX. And of course, inclusion is a huge challenge. What we're seeing in certainly these kinds of citizen science projects is that a lot of the participants are still the usual suspects. So highly educated white men who like to tinker and solder. Getting other people involved, which is one of our goals by actually going for projects on smartphones, because at least most people have smartphones, so that opens up possibilities to engage other kinds of target audiences that we're not reaching yet. Still, that is a challenge to reach them in the right way. And I think we're just getting started on this. I think there's a lot of room and a lot of necessity to experiment and innovate what all this citizen science can still mean. There's a lot of people that are trying to define what exactly citizen science is or should be. I don't care about the definition. Let's figure out together what else citizen science can be. So that's why I'd like to challenge you here as well. So open for questions and discussion.
Okay. Thank you so much for this presentation. Yeah, we encourage you guys to ask any questions you like. Raise your hands or just leave the questions in the chat and just start talking. Sorry.
Okay, so I have a question about the citizen science group of people. You told us that you have a network of citizen scientists, I would say. And how long does it take to create such network and people that are willing to take part in different kind of projects?
So let me answer for iSPEX, and then Hester can answer for some of the newer projects. So for iSPEX, we got kind of lucky that we won this award, because the day after we won this award, we were all over the news, in the newspapers and in on TV, and a lot of people saw it, and we were clever enough that we had our website up and running, that people could register right away. So within one day, we had like 10,000 people who wanted to participate. And also with iSPEX, we had some targeting partners. So we worked with the Dutch Lung and Asthma Foundation, of course, is representing a very clear target audience, and we're working with a popular science journal. So for several target audiences, we would actually either send the iSPEX unit for free upon registrations, because it's really low cost. Or in some cases, we would just have people register and pay a few euros, and then we would send it over as well. And those are actually the people who are really motivated, because they put down a little bit of money, even though it's a few euros. And a lot of these people, so the iSPEX units was done in March. The iSPEX app was done in March, but it was just cloudy and rainy for March and April and May and June. And then people have been training and waiting for all of these months, and then finally the weather got nice, and everybody was just rushing to go outside, because the weather was nice, but also because finally we could do this experiment. And we found that lots of people, actually for years after, would take iSPEX on vacation and do their own little experiments on the bike ride and measure close to a highway and further out. So once you have them, they will stay engaged, at least a particular subset of the participants. We also had quite a number of people who were just ready to go on the hype. They provided a couple of measurements, and then they moved on to the next thing. Hester?
Yeah. Yes, I could answer this question on a number of levels, but maybe to short it down. Actually, what we saw for Measure Together is that the number of participants kind of doubled each year. We started in 2016, 2017, and roughly every year the number of people in the Netherlands doing measurements, which reported to us, doubled. So that went very quickly. So and for example, we had this small town, Meijerijstad. This is really a small rural community. And I saw the kickoff meeting in December, and in March they were having 80 people in the village doing measurements. So this is so rapidly. We as an official institute would still be having meetings about it, and they were already having the sensors up and running. So that can be really fast. So what it boils down to is, it's not difficult to find people. It's not difficult to find citizen scientists. It's not difficult to find people who want to participate, whether it's iSPEX or other types of. That's not difficult. What is difficult is to find the experts that want to participate, that want to look at it in a serious way. And that is really the challenge. It's us scientists that are difficult to get to move, and not the citizen science itself.
Okay, thank you very much.
Okay, I think I had a question about sensors, more of a citizen side. So as you Frans said, the iSPEX sensor was like few euros for everyone. But I've done some initial research before the meeting, and I also found probably iSPEX 2, which you state that the cost will be about 100 euros. Is it correct?
No, that's not correct. We still have some manufacturing issues. That's still the leftover from COVID. It is still quite a bit more low cost than that. But we have to figure out the business model, because we will now deliver actually tailor-made to the smartphone. So you can order so many for this smartphone and so many for that smartphone, which means that the business model is really set up for groups of people and initially research groups to do these kinds of local experiments. Okay. And we have to lower the cost on some of the components for iSPEX2. So it's not officially on the market yet. So I cannot tell you a target price, but the goal is still to leverage the fact that your smartphone already has a very good camera, has all the processing power, has the internet connection and everything, but just add a little bit of very dedicated plastic to be able to do the measurements.
Okay, because like my question was really, do you if the price is going to be higher, but you've already answered that, do you expect some problems or like less engagement from the citizen side?
Yeah, so that's part of the business model. So right now for iSPEX2, because we had in our project, we had scheduled all kinds of validation experiments and citizen science experiments, but then COVID happened, so that didn't happen. So this is still part of the project that we need to do. So for now, we're really focusing on existing groups and existing research groups to do these kinds of measurements. But once we have a validated results from that, then we can open it up further. But the goal is absolutely to keep it as low cost as possible, and also to keep it as easy as possible to do these kinds of measurements.
Okay, thank you.
Yeah, they should also not be too cheap, and because then the commitment of people drops. But if something, yeah, for example, with iSPEX, we had some people who got the iSPEX instrument for free, and they were less fanatic in doing the measurements than the people who actually had to pay for it. So sometimes for free is not better than paying at least a little bit. For the commitment, is better that something has value that can be expressed in money or in effort. That also works. If you put a lot of effort in building an air quality measurement kit, you are also going to be you're going to do more measurements.
I have one more question according to people and citizens, actually, and if they are buying those air quality kits to measure, are they in any way obliged to take measurements on specific days, or is it like just volunteer work? Because I'm wondering if you were waiting for 3 months in iSPEX for the first measurements, how does it happen that everybody on the same day was able to make the measurements?
So for iSPEX, that's because that's how we organized it. I mean, we really marketed this as a scientific experiment to have a lot of people on the same day doing the measurements. But also, I mean, the measurements have to be done without clouds. So there's only very specific days where you can do that. But you can build up the tension, and people start associating doing the measurements with going out on a nice day. But certainly people, after that one measurement day, a lot of people started, whenever the weather was suitable at their location, whether that's in the Netherlands or wherever they are, they just started going out and doing their measurements. They could kind of collect their own measurements and compare from day to day or from location to location. And this really shows that citizen scientists are really scientists, right? They're doing experiments, they're raising hypotheses and testing them. And that's fantastic, right? I mean, we can explain them and tell them to do this measurement here and there, but once they start using their own brains, then real results and unexpected results will come out as well.
Yeah, so essentially they are not doing the measurements for us. They are doing the measurements because they want to know the results. So they're doing it for themselves, which is a much stronger motivation.
And as because here, even on this slide, there's information that there should be feedback or rewards. So what was the feedback and reward on both projects?
So for iSPEX, the real feedback really took us a couple of months to process. And the feedback came in the form of the reward, which was the scientific publication that all the participants were co-authored to. But of course, on little technical issues, the feedback loop should be much faster. So we had a lot of communication with people who were already trying something and something went wrong. We could provide technical feedback right away. But indeed, as Hester says, people are participating because they want to know something. So you have to tell them, if you're sitting on that information, then you have to tell them as soon as possible. Even better, once your sensor has been properly validated and calibrated, get out of the loop and have them get immediate feedback from the measurements itself.
Yeah, so there could already be a dot on the map with a nice color. That is, you know, to see that your results are there on the map. That is already such a kick to get that. I still feel that myself. If you see my measurements, sometimes I have a lot of sensors at home. And if I see them on the map, it's like, oh, that's cool. Yeah.
Okay, thank you very much.
If we are already on the topic of like rewards and we are on this slide, can you explain maybe what happened that there is no gamification point?
So this is more a general lesson learned also from like galaxy zoos, so from the astronomy community. There's a lot of classification kinds of citizen science. And there's actually been a lot of research into motivation of people participating in those kinds of citizen science. And they actually found, also to my surprise, is that the best scientific results and the best motivation is when the participants are being taken seriously. So you don't gamify the thing, you don't turn it into a Pokemon or a Candy Crush kind of thing. It's real science, so don't dumb it down with games or whatever. Never ever underestimate the participants. They have good brains.
Okay, that's surprising for me because I thought that gamification may be a good tool for it, but
it really depends on your target audience, right? But then you get an audience that is there to play the game, and there's some science that happens to come out, but they don't really care. The people who really care tend to be the really useful, meaningful people that really bring results, and they bring their own brains, right? In astronomy, there's this famous result of somebody participating in one of these galaxy zoo classification schemes, and she became very good at it. She was a Dutch school teacher, and at some point she was looking at data and she asked the question, "Hey, what is this green dot here on the image?" And nobody knew. So also my colleagues, they didn't know. So that started up observations with the Hubble Space Telescope. This is now the largest object in the universe named after a single person. Is called Hani's Voorwerp, which is named after that one citizen scientist who asked this question, "Hey, what is this?" and really used her brain. And I think this is a very good example of what we need to facilitate better.
I understand. Thank you.
As I guess what I learned from citizen science is listening. You have to listen to the people. Why? What do they want to know? Why do they want to know it? How can the data help them to answer their questions? And this is really very important, and it's also very difficult. But if you do it like that, then the project is the most successful.
Okay.
So don't do it top down, right? Don't say, "Oh, I'm the scientist. I found a wonderful project. I tell the people what to do and they will do it." You can do that, but you have to be very lucky. The better way is to start talking to people like, "Hey, what is the problem?" I'm also doing citizen science with noise measurements. And then we went to the people, we gave them noise meters to measure sound meter. And we asked them, "Okay, what is the problem? What kind of questions do we have to ask you about airplanes, for example, or trains? what is the problem with this sound? What kind of noise is actually the most bothering to you, and in which way? And once we got the questions properly, then you can do the research, and then you're asking the right questions to these people. Because people, normally a scientist would say, oh, I can only get reliable noise measurements if I have a yearly average. But people don't suffer from yearly averages. They suffer from a plane or a train passing by in a couple of minutes. So it's just citizen science is a brilliant way to do it that way. Just asking people, hey, what is the kind of question? What is the kind of data we should really get to answer your questions, to address your problems?
Okay, so citizen must have the voice in the project. What do you think?
That has a huge benefit.
And not just a voice, a leading voice, like a full 100% stakeholder.
Okay.
Okay, then I propose we should be wrapping up this meeting. Thank you so much for your lecture and all the amazing information you've given to our participants. I'm sure it will be proven very, very helpful. So that's going to be it for today. Once again, thank you everybody for coming, and have a good day.
Yeah, thanks for having us.
Yeah,
Okay,
of
thank
course.
All right. Bye-bye.
Bye.
Bye.
Thank
Bye.
you. Thank you very
Bye.
much.
Thank you.
Thank you. Goodbye.
Thank you
Good
very
luck.
much. Bye.
Have fun. Bye-bye.